In this lecture, we are going to deal with registers available in ARM microprocessor. In ARM microprocessor, there are 17 general purpose registers in a particular operating mode. They are known as R0 to R16. These are the registers generally available in ARM microprocessor, right? And here in ARM microprocessor, there are 6 operating modes known as user mode, supervisor mode, abort mode, undefined mode, normal interrupt mode, and fast interrupt mode. So what do you mean by processor operating modes? Normally when you are executing a normal application, processor will be in user mode, and let us take, say you are resetting the processor will move from user mode to supervisor mode. Similarly, when the processor is trying to fetch some data from a memory and it is unable to get the memory data, so the processor will move from user mode to abort mode. Then in some other cases, processor is trying to execute an undefined instruction, so the processor will move from user to undefined mode. Similarly, when the processor is trying to execute a normal interrupt request or fast interrupt request, the processor will move from user to corresponding interrupt mode. So the more details regarding the processor operating modes I will be explaining in the next lecture. If you want to get more details, you can go through that. Now you understand that there are only 6 operating modes. These are the operating modes. So normally the processor will be in user mode. Based on some interrupt or based on some exceptions, it will be moving from normal mode or user mode to the corresponding operating modes, right? And here you can see that in the user mode of operation, all the 17 registers, in addition to the 17 registers, one more register is there. It is known as CPSR, that is current program status register. It stores the status of arithmetic or logical instructions such as say carry bit, 0 bit, etc. Right? So all the status bits will be available in CPSR. Again, more details about the CPSR register we will see later. Right? So in user mode, all these registers are available. But when the processor is moving from user mode to supervisor mode, you can see that R0 to R12 registers are the same copy of R0 to R12 register in user mode. But this R13, R14 and SPSR, these are new registers, or the R13 and R14 register of user mode will be replaced with R13 underscore SVC and R14 underscore SVC. Then one more additional register will be there. It is known as SPSR underscore SVC. SPSR known as saved program status register. What is the function of this? We will see later. So in supervisor mode, you are having another set of these 3 registers. All the other registers remain same as in the user mode. Similarly, when the processor is moving on to abort mode, here also R13, R14 and SPSR, these 3 registers are a separate registers known as R13 underscore ABT. This underscore ABT shows that these are the registers of abort mode. So here also these 3 registers are separate registers, but the remaining registers are same copy of user mode, right? So whenever you are moving from one mode to another mode, the registers with this dashed line will be new set of registers which are replacing the corresponding register in the user mode. Let us take in interrupt mode. This R13 underscore IRQ and R14 underscore IRQ is replacing actual R13 and R14 of the user mode, right? So whenever you are moving from one mode to, and in fast interrupt mode, you can see these many registers are replacing the corresponding registers. That is from R13, R8 to R14 registers are replaced here in fast interrupt mode, right? So there are certain registers which are available only in the corresponding mode, that is shown by this dashed line. So these registers which are visible only in the corresponding mode of operation is known as banked registers. B-A-N-K-E-D, banked registers. Right. So these banked registers are only visible when the processor is in the corresponding operating modes. Right. So there are total 17 banked registers, including this 5 SPSR. So here also you can see that the SPSR available in each operating mode is a separate one. That is why underscore ABT, underscore UND, underscore IRQ, etc. it is given. So including this 5 SPSR, there are total 20 banked registers. So there are 20 banked registers which are available in the corresponding modes of operation, right? And there are 17 registers which are not banked, right? So these are the registers available in user mode. So total 17 registers plus this 20. So total you are having 37 registers, right? So out of this 37 registers, these registers are available only when you are in corresponding mode of operation. That is why these 20 registers are known as banked registers, and then other than that you are having 17 registers in the user mode. So total 17 plus 20, 37 registers are there, right? Then what is the use of this SPSR and CPSR? CPSR stores the status register, status bits such as carry bit, 0 bit, etc. What is the use of carry bit? Carry bit will be set whenever there is a carry generated when performing arithmetic or logical operation. So carry bit will be set showing that there is a carry generated at the time of arithmetic or logical operation. So like that few status bits are there. Those status bits are present in the register known as CPSR. But in the supervisory mode you can see that CPSR is not there. So in all these registers CPSR is not there. So let us take you are in abort, processor is in abort mode, and standing in the abort mode, let us take it needs to access the status bits. So what does normally what does a processor do? It should move from abort mode to, it should go back from abort mode to user mode, or it should switch the mode from abort mode to user mode. Then only it can access the status bits. But what will be the problem? For switching this mode, the processor need to do some processes. So it will affect the performance of the system by switching the mode. So in order to avoid that mode switching, what they have done is they have given a separate register known as SPSR for each mode. So whenever you are moving from one mode to another mode, whatever content is there in the CPSR, that will be copied onto the corresponding SPSR. So when you are in undefined mode, the content of CPSR in the user mode will be automatically copied to the SPSR. Right, content of CPSR will be automatically copied to the SPSR. Right, so that is how it is done. And the whatever status bits you need to do access here, you can directly access from the SPSR itself. Right, so no need of switching back from one mode to the user mode or to the other mode. Directly by reading the SPSR itself, you will get the same status bits what is there in the CPSR. So that is the advantage of using SPSR in different SPSRs in different modes. So whatever CPSR content is there, that will be stored onto the SPSR, and whatever modification you are doing in the supervisory mode, the SPSR content only will be modified, the CPSR will be as it is. So let us take you are in supervisory mode and you are performing some calculation, and say 0 is getting as a result. So 0 bit of SPSR underscore SVC will be set. It won't affect the CPSR. Right. So that is why the whatever content of CPSR is there, that will be copied on the corresponding SPSR, and if in that particular mode, any changes there in the status bits, only the SPSR content will be modified. CPSR content will not be modified. So that is the advantage of using separate SPSRs. Right? Any doubt? Then you can see there are 3 special registers available in the ARM. So we have told that the ARM is having registers from R0 to R15, that is total 16 registers are there. In the 16 registers, R13, R14 and R15 are having special functions. So R13, R14 and R15 of all the registers are having special function. What is it known as? R13 is also known as a stack pointer. It is having a special function of stack pointer. R14 is having a special function. It is known as link register. R15 is known as program counter. So these 3 registers are having additional function or special functionality of stack pointer, link register and program counter. Then we will see each one in detail. So first one is known as R13, it is known as a stack pointer. So what do you mean by stack pointer? Stack pointer always points to the top of stack. So what do you mean by top of stack? Or what is the use of a stack pointer? Or what is basically a stack? Stack is nothing but a memory area. When it will be used? While you are moving from main program to a function. So let us take you are having a main program like this. The execution will be like this, and let us take inside the main program at this point you are having a function call. Say you are calling a function f1. So what will happen? Main program will keep on executing like this. When you are executing a function, it will move from the main program. Processor will move from main program to a function that is to be executed, right? When you are calling a function, processor will move from the main program to the function. Then it will keep on executing the function, right? So when the processor is moving from the main program to the function, what will happen to the variables you have calculated here? Let us take you are having an intermediate result that is stored in a register known as a R0. You are having an intermediate result. So before moving from main program to a function, content of R0, that is the intermediate result, should be pushed onto the stack. What do you mean by push? When you are storing something onto a stack, it is known as push. When you are reading something back from the stack, it is known as pop. Right? So let us take before moving from the main program to a function, you need to store the intermediate result somewhere. In my case, my intermediate result is there in R0. I need to store this somewhere. Where will I store that? That intermediate result will be stored in a memory area known as stack. And to which location in that stack I should store? To the point where stack pointer is pointing to. So the address location where the stack pointer is pointing to is known as top of stack. So wherever stack pointer is pointing to that location only you will be storing the intermediate result. So now initially the stack pointer was like this. After pushing the last data, stack pointer will get incremented to the next location automatically, right? So stack pointer will be here, and in the next push operation the result will be the intermediate result, which is so if you are writing push R0, R0 content will be stored onto the stack where the stack pointer is pointing to. So the stack pointer will give the starting location of the stack, or the latest location of the stack will be pointed by the stack pointer. So stack pointer points to the top of stack. Top of stack is the latest point where you have stored the data, right? So that is a function of stack pointer. So whenever you are moving from a main program to a function, you need to store the intermediate result somewhere. That intermediate result will be stored in a memory area known as stack, and to which location in that memory area you should store the intermediate result? is decided by the stack pointer, right? So R13 is having a special functionality known as stack pointer. So stack pointer holds the address of the location, because each location will be having an address. You are referring to each location with the help of address. So stack pointer will hold the address to which the next data has to be stored. That is known as the top of stack. So stack pointer is a pointer holding the address to which next data has to be pushed on to. Then R14 is having a special function known as link register. It is also known as link register. So what does the link register do? Link register stores the return address. So what do you mean by the return address? So same example we'll take. You are having a main program and a function. You are executing the main program. When you are calling a function, you need to go to the function. Then processor will be executing the function. After executing the function, the processor should come back to the address, right, or come back to the next address from where you have jumped to the function. So that address is known as the return address, right? So when you are executing the main program, the next instruction address will be present in a pointer known as program counter, right? So when you are executing the program counter value is known as a return address. So that return address should be stored somewhere. Otherwise, after executing the function, processor will not be able to know to where it should come back. So you are executing a main program. At this point, you are going to move to a function. But before moving to a function, the next location should be stored somewhere. So this location, you will be coming back after executing the function. So that location is known as a return address. So after executing a function, to which address the processor should come back or return, that is known as a return address. So before jumping from main program to a function, this return address should be stored somewhere. So where will you store the return address? That is the function of link register. So link register keep track of the return address. So whatever return address you need to store, that will be stored in the link register. Right. So before moving from a main program to a function, the address or the return address to which you need to come back should be stored will be stored in a register known as link register. So that is a function of R14 or link register for storing the return address to which the processor should come back after executing a function. Then R15 is also having a special function. It is known as program counter. What does program counter do? Program counter points to the next instruction that is to be executed by the processor. It points to the next instruction. So let us take this is your program memory. For time being, I am using only 8-bit program memory. That is why the address is of size 8-bit. In ARM, it is actually 32-bit. For explanation, I am using 8-bit. So let us take this is a program memory. You are having some instruction like this. So your processor has executed instruction 0, 1, 2, 3, etc. Next, the processor should execute the instruction present in 0x04. So how will the processor identify that this address location or this instruction is to be executed? That is done by the program counter. So program counter will contain the address of the memory location that is to be executed by the processor in the next cycle. So here program counter is having 0x04. So after executing all this instruction, the processor will go to the 0x04 address location which is pointed by program counter and it will execute this. How it is getting executed? By taking it to the register known as instruction register. So whatever instruction that is to be executed will be present in the instruction register. So how will the processor get this instruction? By using the program counter. So program counter always points to the next instruction to be executed. So after executing 0x04, or after taking this to the instruction register, what will be the content of program counter? It will be automatically incremented to 0x04, 0x05. So when the instruction present in 0x04 has been taken to the instruction register, automatically program counter will be incrementing to the next instruction. So whenever you are executing an instruction, automatically program counter will increment to the next location that is to be executed. That is why program counter is set to point to the next instruction that is to be executed. Right. So these are the additional or special functions of R13, R14 and R15. So in general, so when you are combining all these things, ARM is having total 37 registers of 32-bit each. Out of these 37 registers, 20 registers are visible only in particular mode of operation. So those 20 registers are known as banked registers, BANKED. And the remaining 17 registers are the general registers, starting from R0 to R15, that is 16 registers, and one more register known as CPSR. Right. So how are these 37 registers splitted up? There are 30 general purpose registers. Right. There are 30 general purpose registers. Then 5 saved program status registers, that is in each mode except the user mode you are having SPSR. Then one CPSR. Where is the CPSR available? CPSR will be available in user mode only. In all the other modes you are having SPSR. Then one program counter. Program counter will be available in all the modes. That is same program counter will be available. So you are having one program counter, one CPSR, 5 SPSR and 30 general purpose registers such as R0, R1, R2, etc. So total 37 registers are there. Then next we will see in detail about the CPSR. So this is the CPSR register content. So since ARM is a 32-bit register, all the registers are of size 32-bit. So CPSR is also having, or a CPSR is also a 32-bit register. What do you mean by CPSR? Current program status register. So I told it stores the status bits. So in CPSR there are two sections known as, or two fields known as condition field and control field. So these 4 bits are known as the condition flag fields or condition fields. What does it contain? 4 bits. N, Z, C, V, Q. So N stands for negative flag, negative condition flag. When this bit will be set, so all these bits can be either set or reset. So when does this negative flag bit be set? Negative flag bit will be set when the ALU is performing, or after performing a certain arithmetic or logical operation, ALU is generating a result as negative. So whenever as a result of an arithmetic or logical operation, if we are getting a result as a negative number, then this N bit will be set. Then when the Z bit will be set, Z stands for 0 flag. So similarly, whenever the ALU is performing an arithmetic or logical operation, and when the ALU is getting a result as 0, then 0 bit will be set. So what are the arithmetic operations generating 0 result? When you are subtracting two same numbers, 1 minus 1 is 0, 2 minus 0 is 0. Similarly, when you are multiplying 1 into 0, it is 0. So whenever you are multiplying a number with 0, result will be 0. So these are the, so and when you are adding 0 plus 0, again it will be 0. So when you are adding 0 plus 0, when you are subtracting same numbers 1 minus 1, when you are multiplying a number with 0, you will be getting a 0 result. So these are the 3 conditions where arithmetic operation is generating 0. Then which are the conditions generating 0? Which are the logical operations which is generating 0? 1 and 0 will be 0. When you are performing 1 and it will be 0. 1 and 0 is 0. 0 or 0 it is 0. 0 or 0 it is 0. 1 XOR 1 is 0. 1 XOR 1 is 0. 0 XOR 0 is 0. 0 XOR 0 is 0. Similarly, when you are complementing 1, you will be getting 0. So these are the logical operations which you are getting 0 result. So whenever an arithmetic or logical operation is generating 0 result, 0 condition flag bit will be set. The next bit is known as carry bit. So let us take when you are adding two numbers and you are getting a carry as 1. So when you are adding two 8-bit numbers, let us take 8-bit numbers as FF. In hexadecimal representation, FF represents 8-bit maximum number. When you are adding two FFs, FF added with FF, what you will be getting? FE with a carry 1. FE with a carry 1. So what is that? When you are adding two FFs together, you will not be able to store the result in an 8-bit number. You will be getting a 9th bit. That is known as a carry. So whenever an arithmetic operation is generating a carry, this carry bit will be set. So that is in the case of unsigned addition. And when you are performing signed addition and if you are getting a carry, V bit will be set. V stands for overflow bit. So N stands for negative bit, Z stands for 0 bit, C stands for carry bit, V stands for overflow. So carry bit will be set whenever there is a carry which is coming as a result of unsigned addition. Similarly, when you are performing a signed addition and when you are getting a carry, then overflow flag bit will be bit. What is the overflow flag bit? It is known as the V bit. So these are the status bits or flag bits. So this field is known as condition flag field. Similarly, we are having another field known as control field. This is known as a control field, right? Control field consists of two sections. One is shown by these bits IFT, and another set of bit is shown by mode selection bits. So what is the use of I bit, F bit and T bit? I bit stands for the IRQ enable or disable bit. So I and F is used for enabling or disabling IRQ or FIQ. IRQ stands for normal interrupt, FIQ stands for fast interrupt. So whenever your controller is getting a normal interrupt, IRQ will be detected. Whenever the processor is getting a high priority interrupt, FIQ will be detected by the processor. So I and F bit is used for enabling or disabling. You should keep in mind it is used for enabling or disabling. So if I bit is set, what does it mean? If I bit is set, it means you are disabling IRQ interrupts, normal interrupts. Right? If I bit is 0, it means you are enabling IRQ. So if I bit is set or if I bit is 1, you are disabling normal interrupt request. If I bit is 1, if I bit is 0, you are enabling IRQ. If I bit is 1, you are disabling IRQ. Similarly, the next bit F. If F bit is set, you are disabling FIQ. In both the cases, set means you are disabling. Clear means you are enabling. So if F is equal to 0, you are enabling FIQ. So what do you mean by FIQ and IRQ? FIQ stands for fast interrupt request. So whenever the processor is getting a high priority interrupt. What do you mean by interrupt? You will understand when you are going for the next lectures. So whenever you are getting an FIQ interrupt will be generated, and if you want to enable FIQ, this F bit should be 0. If F bit is 1, FIQ will be disabled. Similarly, if I bit is 1, IRQ will be disabled. So these two bits are for disabling FIQ and IRQ. Then what is the use of T bit? T bit is used for specifying the state of ARM. Right. What do you mean by this ARM state and thumb state? We will be dealing in the next lecture. So if the processor is in ARM state, T bit will be 0. If the processor is in thumb state, T bit will be 1. What do you mean by this ARM state and thumb state? We will be seeing in the next lecture. No need of worrying now. So in order to specify ARM state, T will be 0. In order to show that processor is in thumb state, T will be 1. Then the next bit is known as mode selection bits. So the mode selection bits shows in which mode of operation your processor is in. If the processor is in user mode, this the mode selection bit, how many mode selection bits are there? 5 mode selection bits are there. These 5 bits will be having a number 10000 if the processor is in user mode. If the processor is in abort mode, it will be having a number 10111. Right? So by seeing the mode selection 5 bits, you can identify in which operating mode your processor is in. Right? Then what is the 0B? 0B stands, it shows that the next numbers are binary numbers. If it is hexadecimal number, you will write it as 0x. If it is decimal number, you will write it as 0D. So 0B shows that it is a suffix showing that the numbers coming after 0B is binary number. Right? So mode selection bits identifies in which mode your processor is in. Right? So these are the bits available in CPSR, and the bits in other than these bits are undefined in this version. No need of worrying about that. So in this, so by using this lecture, we have seen what are the registers available in ARM and what are the modes of operation. And more details of the modes of operation will be available, will be explained in the next lecture. So you can go to next lecture if you want to identify the details of processor modes. Thank you.